Hi everyone, this is Dr. S. Kannappa. I'm presenting the course Digital Signal Processing, Module 3. Module 1 is completely about the discrete time signals and systems, the basics behind digital signal processing, and how we'll calculate the responses of the discrete time systems for a given discrete time signal. And Module 2 is particularly about the transform from time domain signal to frequency domain signal by using a discrete Fourier transform and jet transform. And we have seen the drawback of direct computation of discrete Fourier transform. To directly calculate by using the formula of DFT, it requires more number of computations, more number of multiplications, and more number of additions required to be performed. Hence, the speed will be automatically decreased for computing for larger value of n. Hence, we are going for an efficient method of finding DFT that is called fast Fourier transform. The fast Fourier transform is an algorithm or a method to find discrete Fourier transform. It is not a separate transform. Fast Fourier transform is also to find DFT, but it is used to calculate with high speed or less number of computations can be done for any given n compared to DFT. That's why it is called fast Fourier transform. So in this lecture, we'll cover how FFT is reducing the number of computations and its advantages over DFT, and methods of finding DFT using FFT transform. So there are two types of FFT and also a overview of different radix FFTs, radix 4, split radix FFTs, mixed radix FFT. Just we are going to give you an overview. So here mainly we are covering radix 2 FFT, and its algorithm is performed by using butterfly diagram. So that we are going to discuss about what is butterfly diagram. Different types is DAT FFT and DAA FFT. And so bit reversal is one of the important concepts to understand the DAT or DAF FFT. And then inverse FFT. How we'll calculate the input signal from the given spectrum by using this FFT algorithm, and the applications of FFT. So that covers the importance of the FFT. So if you see the complexity between DFT and FFT, mainly the computations are in the order of n square. For computing DFT, it needs n square computations in the order of n square also. And for FFT, it needs the number of computations are reduced by logarithmic time. So n into log n base 2. So if you see number of multiplications and number of additions by using DFT and FFT. Here in this example, we have taken number of multiplications. For n is equal to 16, it needs n square multiplications to be performed, because we know the formula sigma x of n into wn power k. So x of n is for any given input, x of n is one value at n is equal to some instant, and wn power kn is one value. Like that, the formula contains n is varying from 0 to n minus 1. So sigma n is equal to 0 to n minus 1, that means n samples we are varying x of n, multiplied by corresponding fiddle fact. So n multiplications to be performed for finding one output sample. To calculate n output samples, it needs n into n multiplication. So to find one output sample, it needs to find n multiplications, and the same has to be repeated for finding all the output samples. The output samples also n number of output samples. So n into n, so it needs n square multiplications if you directly calculate by using the formula. That's why it is, if it is 64, 4096 multiplications need to be performed by using DFT. If we calculate by using FFT algorithm, it is n by 2 log n. N by 2 log n multiplications to be performed. But for addition, n log n additions. That's why it is the order of n log n. So for multiplication, it is n by 2 log n. So log n, if n is equal to 64, logarithm of 64 base 2 is, it is around 6. So n by 2 is again 64 by 2, 16. 16 into 6 is 192. Around like n is 64, so 32. 32 into 6 will give 192 value. 192 multiplications has to be performed. When compared to 4096 multiplications, if you directly using the DFT formula. So there is a huge difference in the number of multiplications. So the speed is improved by 21 times almost. And if it is 256, n is equal to 256, 256 square is 65,536. And if it is applied, the same input signal is applied to FFT algorithm to find out the spectrum, it needs only 1024. If you apply n is equal to 256 in this formula, 256 by 2 into log 256 plus 2, we'll get 1024 multiplications only when compared to 65,536 multiplications. So see, 64 times the speed has improved. If we choose n is equal to 1024, then the number of multiplications are very huge, and but if by using FFT it is only 5120. So the speed has improved 205 times. So massive improvement in the speed. When the order increases, when the order is higher value, then the efficiency of FFT is very high when compared to the DFT. For smaller value of n, for 4, n is equal to 4 or n is equal to 8, it may be around 10 times, 5 times improvement only. But if you take n is equal to very high value, it is 205 times, 100 times it is improved. So mostly the image, if you take an image, it needs megapixels. So number of pixels are nothing but we can take number of samples. To find the transform of an image, we need to apply Fourier transform for the signal. To directly apply by using the formula, it needs lot of computations. So speed will be automatically decreased. So if you use by using if you perform by using FFT, definitely the speed will be increased. Similarly, the number of additions are n log n. Here it is, so n into n minus 1. So for number of addition, it is in DFT, it is n into n minus 1, almost it is equal to n square, but here it is n log n. So twice, so this will be twice of this effect. Multiplication, number of multiplications are less than the number of additions. It almost doubles. So what is the basic concept behind this FFT is nothing but divide and conquer principle. What is the divide and conquer principle? So instead of calculating completely for n points, if x of n input contains n points, by using a direct formula, we'll calculate the DFT for all n samples. We'll apply n samples for finding one output, and we'll be repeating the same thing. Here, instead of applying all the inputs signals samples, we'll split the input samples into two parts: even indexed samples and odd indexed samples. So for suppose, if you take this one, index, so input sequence, if you take 8 point, so the 8 samples will be there in the input. So each sample is indexed with n. So n equal to 0 means x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7. It is index only. It has some value. But to read the value, we need index. Here, the input samples are splitted into two parts. So even indexed samples, that is first sample and second sample, fourth sample and sixth sample. 0th sample, second sample, fourth sample and sixth samples are even indexed samples, and odd indexed samples, similarly first sample, third sample, fifth sample and seventh sample. This will be grouped into two parts, odd index and even index, and we are applying for n by 2 point. So n samples means we have n by 2 even index and n by 2 odd index. We are splitting into two parts, and each part is connected to a lower order DFT, that is n by 2 point DFT, as n is divided into two halves. So two n by 2 point DFTs are calculated. So compute n by 2 DFT for even samples, even indexed samples, again n by 2 point DFT for odd indexed samples, and we'll combine these two and we'll perform multiplication of fiddle factor. So one of the output is combined with another output by multiplying the second output with a twiddle factor, and remaining half of the values will be calculated by using this one, addition of first half output with the product of second half with twiddle factor. So here n by 2.2 will calculate. Remaining n by 2 will calculate by simply subtraction. So already we have calculated this product. Second output u of k multiplied with twiddle factor, and it is available. That product is available. That is subtracted from e of k to find the rest of the n by 2 samples. So totally n samples we can calculate. So here, instead of multiplying n times, we'll multiply only n by 2 sample, n by 2 times 1. So in one stage, we'll multiply n by 2 times. We'll perform n by 2 multiplications only. And here we are adding, subtraction means again it is addition only. So here n by 2, n by 2. So n additions has to be performed. In one stage, in one iteration, we'll perform n additions and n by 2 subtract, n by 2 multiplications. Right? And we'll repeat this process. This n by 2 is again split into another two halves, even and odd samples. So it is a recursive process. Again, we'll perform in the second iteration, we'll perform half n by 2 means n by 4 multiplications and n by 2 additions. Multiplications will become half, but additions are same. N point means n additions. If it is n by 2 point means n by 2 additions will perform, but multiplication will be n by 4, half of the n value. Like this, it will be repeated until the final output is obtained. So in every stage, in every iteration, the multiplications is going to be reduced by half. And also the number of stages we are going to perform is logarithmic number of stages. We are not going to perform n stages, n times we are not going to repeat. We are going to repeat only log n times. That's the advantage. That's how we'll reduce the speed. We are reducing the number of stages, and also we are reducing number of multiplications in each stage. So if we have log n stages, we will get logarithm times of n. If it is n equal to 8, then log 8 base 2 is 3. So we'll get 3 stages one. Within 3 stages we can compute. Hence 3 multiplied by, in each stage we will multiply n by 2 multiplication. So 3 multiplied by 4. So only 12 multiplication will perform. But if you take n square means 8 square, 64 multiplication will perform. So two way we are vertically as well as horizontally we are reducing. Horizontally when you are moving with number of stages, the number of stages are confined to log n. When vertically we are calculating all the outputs, so the number of multiplications are half only. So that's why the multiplications are n by 2 log n, but additions are n log n. So that's how the computations are reduced. Now let us see two types of FFT algorithms. One is DAT FFT versus another one is DAFFT. Decimation in time and decimation in frequency. What is decimation in time? As we have discussed, this FFT is calculated by splitting the input sequence into odd indexed and even indexed. So two groups we are forming. We can do this splitting, so reducing the length of the samples means it is decimation. So we are doing decimation in input sequence and we are applying the DFT. In the same manner, we can perform decimation of the output samples also. From the reverse order we can perform. We can divide the output into two parts and we'll calculate it. So we'll calculate even indexed output only and then odd indexed output by using two n by 2 point DFTs. Again, this n by 2 point DFT is, again it is divided into n by 4 point. In under n by 2 values, we will calculate n by 4 odd indexed outputs we will calculate first. Next, n by 4 even indexed output we will calculate. So likewise, we'll calculate outputs by splitting into two parts. In decimation frequency, in decimation time, we'll apply the inputs with two groups and we'll calculate all the outputs. Okay. So here we'll apply input into two groups and we'll calculate all outputs. But here in decimation frequency, we'll apply all inputs and we'll calculate only even indexed group and odd indexed group output separately. Output is splitted, here input is splitted. So that's why two methods we can perform. So decimation time, decimation frequency. Okay. So in decimation time, so that as I told, input is time, or in DFT output is frequency. So input is bit reversed order. When you keep on doing splitting of the input samples into two parts, even and odd, from one stage to another stage. So finally, in the final flowchart, final overall, if you do final, all the stages are completed and we are getting a complete procedure. By the time log n stage finish, the input order is changed because we are converting even samples and odd index samples. Again, we are in even index samples, we are splitting into even and odd. And in odd, again, we are splitting into even and odd. So finally, the input order will be changed. So that order is, it can be derived as bit reversed order. So in decimation time, the input sample we are applying is in bit reversed order, but the output is normal order. As we are telling, we are calculating all the outputs at a time, but input we are applying in the groups. That's why the input order is changed. And similarly, in decimation frequency, we are grouping the output into two parts. So output is order will be changed from stage to stage. So final, by the time end of the FFT algorithm, the output order is bit reversed because output is grouped, and input we are applying as it is. So input is in the natural order. Natural order means so ascending order. X of 0, X of 1, X of 2, X of 3 up to X of n minus 1. Now, what is this butterfly? Butterfly diagram Let's see the butterfly diagram, and then we'll go for the what is the difference between the butterfly diagrams we are using in decimation in time and decimation in frequency. So let us see this butterfly diagram, and then we'll discuss the difference between these two. So if you see the butterfly diagram, how we have discussed, so how this is splitted. So if it is 8-point DFT you want to calculate, we are supposed to calculate. We are splitting this 8-point into two 4-point combinations. So this is 4-point DFT, it is another 4-point DFT. And if it is again this 4-point DFT is not directly computed, we are combining it into two 2-points DFTs. That means the input is grouped into all 8 inputs are grouped into even index and odd index. Similarly, this 4 is grouped into two even indexed, odd indexed, two inputs. Again, this is divided into even index and odd index. So finally, we'll get the input sequence will be x of 0, x of 4, x of 2, x of 6. This is bit reverse order. So 0, if 0, 0, 0, 0 is represented in binary form. So let's check here. So this is bit reversal order. So 0 means 0, 0, 0. If you reverse the bits, we'll get 0, 0, 1. So bit reversal order is 0, 0, 0. And if it is 1, index is 1, it is represented in binary 0, 0, 1. So as it is 8 samples, we'll represent with 3 bits. If it is 16 samples, we'll represent with 4 bits in 2 powers. So 0, 0, 1, if you reverse, we'll get 1, 0, 0. This value is 4. So index is changing from 1 to 4 because of converting it to even and odd index. 2, if you do bit reverse 0, 1, 0, you'll get again you get 0, 1, 0, 1. 3, if you bit reverse 0, 1, 1, it will be 1, 1, 0. And 4, if you reverse, will get 1, 0, 0. Reverse means 0, 0, 1. Will get 1. So if you observe, after bit reversal, completely the first half is even index samples and second half is odd index samples. Right? So this is bit reversal. So let us see how this butterfly diagram looks like. So this is the process of divide and conquer approach. Now let us see the individual 2-point DFT, 4-point DFT and 8-point. So this is the basic butterfly diagram, 2-point DFT. Input we are applying one sample, here we are applying, here another sample we are applying. Before this, as I told, the output half of the values are calculated by adding the first input plus the product of second input and twiddle factor. This is added. And similarly, the second half is calculated by subtracting first input and the product of second input and twiddle factor. So twiddle factor we are multiplying only once because we are calculating 2 points, but we are multiplying only one time the twiddle factor, input multiplied. And we are performing addition 2 times. So as it is addition, we are multiplying this input with -1. So it is just sign change and it is added. It is not multiplication, subtraction, it is addition because here already it is multiplied with -1 and hence it will become minus b w n for k. This dot combining point is indicates addition only. Okay. So next, if you see 4-point DFT, so this up to this one is 4 point. So 2.2 2 points are combined. Now this is one group and this is another group. So lower group will be multiplied with twiddle factor and this twiddle factor multiplied value will be added with the upper values. Similarly, this one, so first branch in the upper, first branch in the lower are combined. Second branch in the upper group, second branch in the lower group are combined for addition, and similarly for subtraction. When downward line indicates the subtraction, subtraction means multiplying the second operand with -1 and addition with the first operand. If you go for 8-point, so now this one group, 4-point output is one group and another 4-point output is one group. So the lower 4-point output groups are multiplied with twiddle factors and corresponding lines are added. First line in the upper group, first line in the second group are added, and similarly second line, third, fourth are added to find the half of the values. Subtraction, after subtraction we will find the another half of values. So likewise, so this is called the butterfly diagram. In decimation time, if you see, the Tudel factors are multiplied, so before the butterfly stage, we will multiply. But if you take DAF, it will be in the opposite direction. So now let's finalize the DFT and its order and butterfly. So butterfly will be multiply in decimation in time, multiply after addition. So it's multiply before the addition. Actually, decimation time, before addition we will multiply, and then we will perform addition. But in decimation frequency, will multiply after the addition. It's slightly changed. So in decimation frequency time, the will add before, so we'll multiply before addition. See, this is multiplication. So this multiplication we are performing before the, so here the meaning is after addition we'll perform Tudel factor. So again after addition we'll perform Tudel. So first Tudel factor is ignored, but actually if you start from beginning, we'll multiply before the stage, butterfly stage. Here before we'll multiply the butterfly stage. Here before the last stage we'll multiply the butterfly Tudel factors for the butterfly diagram. So similarly, decimation, input is decimated and output is decimated in DA. So complexity is, as we have discussed, n by 2 log n multiplications. Here n by 2 log n. So both are same. The computational point of view, both decimation time and the decimation frequency both are same. Only the difference is the order we are performing. In stages, log n stages it contains. It also contains log n stages. So if you see this one, n is equal to 8. So log n, log 8 base 2 means 3 stages. This is stage 1, 2-point butterflies, and this is stage 2 for 4-point butterflies. This is stage 3, 8-point butterflies. You can observe in every stage 1, 2, 3 and 4. 4 times we are multiplying. Here also 4. Here upper 2 times, here it is 2 times. Here it is 4. So in every stage we are multiplying n by 2 times multiplication. So number of stages are log n. So n by 2 log n. Now let us see how this diagram is derived. So we have seen the procedure, but how mathematically it is derived, functionally how it is validated. So this is a simple derivation for decimation time algorithm. So we'll consider n is equal to 2 power m. So as we are discussing radix 2-point FFT, the number of samples in input capital N must be in 2 powers. N must be in 2 powers. So we always take number of samples must be either 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and so on. So 2 point, 4 point, 16 point, 32 point, 64 points and so on. So it is not possible to find out any other n values. So if you take, if it is not in the 2 powers, so it will be converted into 2 powers by adding dummy zeros, extra zeros in the input sequence. Like yeah. So we'll see how mathematically it is derived. So if you take n is capital N is the number of samples. That number of samples must be in 2 powers. So for performing radix 2 FFT algorithm. So as we said, x of n sample is divided into 2 parts, 2 sample groups. So f1 of n and f2 of n. So f1 of n is even indexed sample. So x of n is input sequence. X of 2n is even index and x of 2n plus 1 is odd index. So if you take n is equal to 0 up to n by 2 minus 1, here it is n is equal to 0 to n by 2 minus 1. So this is overall n by 2 minus 1. This is another n by 2 minus 1. So total n n samples will get 0 to n by 2 minus 1. It's this n by 2 samples. This is another n by 2 samples. Total n samples. So if it is applied to DFT, now we are grouping into two n by 2 point sequences, and it is given to N-pont DFT. So this is combining these two N-pont DFTs. So 0 to n minus 1 x of n wn for kn is the formula for N-pont DFT. As we are converting x of n into even and x of n into odd index samples, it is split into two parts. This is even is off and odd is off of the n samples. So x of n even means x of 2m. So instead of using n, I'm using m to avoid the confusion between n and m, because wn for kn is having n, so that's why it is with m, where considering the index can be represented. So m is equal to 0 to n by 2 minus 1 x of 2m. You can use n also, no issue, but for avoiding the confusion we are using this 2m. So x of 2m into wn power k power 2m. N is replaced with 2m, and here n is replaced with 2m plus 1. So here the even index samples are having half of n samples, so n by 2 samples, so it is varying from 0 to n by 2 minus 1. Here also the odd number of samples, odd index samples are having n by 2 samples, so that's why it is having some 0 to n by 2 minus 1. So if you split this term into two parts, wn power k 2m into wn power k. So wn power k is independent of m. The summation is varying under m. So this can be separated. Wn power k into sigma m equal to 0 to n by 2 minus 1 x of 2m plus 1 wn by 2 power km. So this is one n by 2. So it is in the form of n by 2 point DFT. So we know the formula for n point DFT, some sequence into wn, capital N, so wn power kn. So if it is n point DFT, capital N point DFT, we will get w subscript capital N. But if it is n by 2 point DFT, we must get w subscript n by 2. That's why w n power 2 km can be equivalently represented as wn by 2 power k. So both are same, because e power minus j 2 pi by n. Okay. So n by 2, again it will goes to numerator, 2 pi into n only, 2 pi into 2 only. So that's why this 2 will come. So it is equivalent, wn power k into 2m is equivalent to w n by 2 power km. So now we can say it is in the form of DFT, where m is varying from 0 to n by 2 minus 1, some sequence into wn by 2 power k. So it is n by 2 point DFT. This is another n by 2 point DFT, but the input is even index samples here, but here the inputs are odd index samples. So this can be represented as, now this is sigma f1 of m into wn by 2 power km. This is f2, because x of m is divided into f1 and f2. So its DFT is represented with capital F1 of k plus wn power k into capital F2 of k, where F1 and F2 are n by 2 point DFTs. So, but x of k is n point DFT. So n point DFT is obtained by combining two n by 2 point. Here to find 8 n samples, we are multiplying only n by 2 total factors. Here only we are multiplying. For n by 2 point DFT only we are multiplying. So n by 2 total factors, k is varying from 0 to n by 2 here. So this is n by 2 point DFT. So k varies from 0 to n by 2 minus 1. So n by 2 total factor. For every k, we are multiplying with wn power k. So n by 2 point DFT is multiplied with n by 2 total factors. So to find n point in one iteration we will multiply with n by 2 multiplications. So this can be calculated further by dividing f1 into even and odd again. So f1 is divided similarly if you do for f2 of k, f1 and f2 can be calculated by using addition and subtraction of v1 of k and v2 of k. So likewise it can be calculated in a iterative manner. So every time when we are proceeding from one stage to another stage, the computations are reduced further. Therefore, finally, the number of computations are log m base 2 into n by 2 multiplications. So this is the one stage we have considered. In a similar manner, it will be repeated for every stage. Right? So this is another stage we have considered and we have done similar manner, multiplying half of the DFT and it is added with the another DFT. So likewise we can get this. So 2 4 point already this is 2 4 point. This 4 point we have obtained, and how this 4 point is obtained means even index samples are applied here and odd index samples are applied. So this is this value is multiplied by Tudel factor. So this is added with this one and this subtracted and added with the shape. So this next butterfly diagram by using DFT. In DAT, as the same way, we will multiply half of the DFT with Tudel factor and it is added with the first answer. So see, this 8 point is grouped into 2 4 point. This 4 point DFT we are not calculating using butterfly. Just assume it is the block box. So here we calculate one output and this block box will calculate one output. So this output is multiplied with Tudel factor. Second half output is multiplied with Tudel factor, and these two are combined simply just by adding and subtracting to get 8 point. Now this block box is removed and it is divided into two points. So we'll calculate, this is 1 2 point. So this is block box now. This is 2 point and this is another 2 point. This second 2 point is multiplied with Tudel factor and it is combined to form a 4 point. Now this block box will be replaced with the, but similarly this is again, this recursive process will be continued. So in the same manner, if you see DAF FFT, what is DAF FFT? In DAF FFT, as we have discussed, this is the basic butterfly diagram for DAF. The basic butterfly diagram for DAF, A, B are input samples, and here the input samples are not multiplied with Tudel factor. After adding and subtract, just will add A plus B will perform. Here it is A minus B will perform. After addition, the subtraction, the subtracted branch, the lower half only will be multiplied by Tudel factor, Wn per Kn. So likewise, so here the output is divided into two parts. X of 0 to X of 7 is grouped into two parts, even indexed samples and odd indexed samples. So these even indexed samples are capital X of 0, X of 2, X of 4, X of 6. Here capital X of 1, 3, X of 5, X of 7. So this is obtained by multiplying, just by combining two 4 point DFTs like this. So this is the addition and subtraction and it is multiplied with it. Now this 4 point is again divided into two parts, two points, and these are added and subtracted and multiplied with the Tudel factor of the lower branch. And again this 4 point in the similar manner it will be divided. How mathematically it is obtained? As we have discussed in the DAT FFT, the similar manner also here also mathematically we can divide the x of k output is divided into two parts. When output is divided into two parts, so see x of k half values 0 to n by 2 minus 1, and another half is x of 2k and x of 2k plus 1. So two stages we will consider, x of 2k and x of 2k plus 1. So how we will calculate this x of 2k means simply by adding with first input half inputs with another half inputs, and odd x of 2k plus 1 is obtained by subtraction. So here we can see this one. So this is a preliminary mathematical steps to obtain this one. So here input x of n wn power kn is divided into two parts. We don't know it is even and odd, just it is divided into two parts, 0 to n by 2 minus 1, it is 0 to n by 2 to n minus 1. So half value 0 to n by 2 minus 1 will take n equal to, and here n equal to n by 2 to n minus 1. So this summation n by 2 to n minus 1 can be replaced with this 0 to n by 2 minus 1 when n is equal to n plus n by 2. So when you substitute n equal to 0, then x of 0 plus n by 2, this is x of n by 2. Here also if you substitute n by 2, we'll get x of n by 2. The same, the lower order, here it is n equal to 0, but we want to get n by 2 sample, so it is represented with 0 plus n by 2. If it is 1, n by 2 plus 1. So similarly, n by 2 minus 1 plus n by 2 means it is n minus 1. So it is equivalently represented like this. So now both the summations are varying from 0 to n by 2 minus 1. So we can commonly represent it as 0 to n by 2 minus 1. But here x of n plus n by 2, here it is x of n. Additionally, there is one trivial factor term separated, that is wn power k by 2 n or n by 2 into k. So this is represented as minus 1 whole power. How it is represented as minus 1 power k? Just simply will represent e power minus j 2 pi by n whole power k into n by 2. So wn power n by 2, it is, this value will be equal to minus 1. wn power whole power n by 2 is simply minus 1. That is e power minus j 2 pi by n into n by 2. n will get cancelled. 2 pi by 2, 2 get cancelled. E power minus j pi. What is e power minus j pi? Cos pi minus j sin pi. Cos pi is minus 1, sin pi is 0. So just simply we will substitute this value in this power in the trivial factor formula. We can obtain it as minus 1. And k is a variable, so minus 1 whole power k. So this is like this. Just we will split into two parts and we'll make it as a preliminary mathematical formulation. wn power kn into x of n plus minus 1 whole power k, x of n plus n by 2. Now if you substitute k equal to 2k, this minus 1 whole power 2k will become plus. When you substitute k is equal to k is equal to 2k plus 1, so that is odd samples, then minus 1 whole power odd will be minus. Okay. So just right. So now therefore, so x of 2k of even output is calculated by adding the input samples, and this is odd is calculated by subtracting the input sample. So this is input sample 0 to 7. The first half 0 to 3 is added with the second half 4 to 7. So to find the even output sample, this is one iteration, and first half is subtracted with second half. This is minus 1. Second half is multiplied with minus 1, so it is negative. It is added with the first half, so it is a minus b form. So subtraction. After subtraction, it will be multiplied with wn power k. So now, so same manner, it is again in 4 point will split it into two. First half is added with the second half. First half is added with the subtracted with the second half, and it is multiplied with the trivial factor. So it will be repeated. So if you say same manner the computations in every stage, so to find 8 outputs, we'll calculate only 4 trivial factors. Okay? That 4 trivial factors are multiplied here. So 4 multiplications only will perform, but additions are 8. N additions, n by 2 multiplication. So we have log n stages. So n by 2 into log n multiplications, and n additions into log n. So n log n number of additions. So the computations point of view, both are same, D80F50 and DAF50. We can choose any method. So now let us see a simple problem where we can solve this stage by stage. We take a sequence 1 1 all ones. We want to find out DFT sorry, using D80F50 algorithm. So just we'll represent this in D80F50 algorithm. We want to represent in the bit reversal order. So as all are ones, just simply x of 0 bit reversal order will take all inputs 1. And before starting this butterfly stages, just we want to calculate the twiddle factors. The twiddle factors, only we need some 4 twiddle factors: W840, W841, W842, and W843. Okay. 0, 1, 2, 3. So W840 is e power 0 is 1. W841 is e power minus j 2 pi by n into 1. So n is 8. So e power minus j 2 pi by 8 is e power minus j pi by 4. So it is equal to 0.707 minus j 0.70. And if it is W842, e power minus j 2 pi by 8 into 2. So it is equal to e power minus j pi by 2. It is equal to pi by 2 means sine is 1, cos is 0. So minus 1 will get. So if it is W843, e power minus j 2 pi by 8 into 3, we will get 3 pi by 4 is again minus 1 by root 2 minus j 1 by root 2. This is used in this butterfly diagram. So if we take first stage, 1 we are applying here, just will combine at this point. 1 plus 1 is equal to 2. Here it is W840 is 1, 1 into anything is 1 only. 1 plus 1, 1, 1 minus 1, 0. The alternative will get 2 0 2 0 2 0. The next stage, this 2 0 2 0 are applied to the next stage. So W840 W842 is multiplied before the stage. So it is minus j, it is 1. So 2 plus 2 will get 4. Here it is 0 plus minus j into 0 0 0 plus 0 0. When we subtract 2 minus 2 0 0. So similarly, say another 4 point also will get 4 0 0 0. For third stage, so just here a little bit we'll get twiddle factors. So anyhow it is multiplied with 0. This twiddle factors all multiplication will be 0. So it is W840 is 1, 1 into 4 4. So 4 plus 4 at this point it is 8. And the remaining all are 0 plus 0, all are zeros. Even while subtraction, 4 minus 4 is also 0. So we get the very easy for computation instead of directly calculating the DFT. So whatever the input they will give, just simply will apply for the FFT flowchart. And the main thing is we want to calculate the twiddle factors appropriately, and we have to substitute in the diagram. Now, so how we will choose this twiddle factors? So this in third stage, this is the twiddle factor. So actually in every stage Wn power k is separated. So simply in this stage Wn power k, but k varies from 0 to n by 2 minus 1. In the next previous stage it is n by 2 point DFT. Here it is n by 2 point DFT. This is n point, here it is n by 2 point. So W n by 2 power k it is. So n by 2 power k can be represented as Wn power 2k. You can write n by 2 power k or Wn power 2k also. So here Wn power 2k. So k varies from only 2 twiddle factors here. It is 4 points. So n by 2 means 2 twiddle factors. K varies from 0, 1. So 2 means. So W8 power 2k. K is 0 means W840. When k is 1 means W8 power 2 into 1. So that's the way we want to choose the twiddle factors. W8 power k in the last stage, nth stage, Wn power 2k in the n by 2 stage, Wn power 4k in the n by 4 stage. So we'll choose k value based on number of twiddle factors, starting from 0 to n by 4 minus 1 or n by 2 minus 1. So now let's say inverse FFT. So this FFT we can calculate by using either DAT FFT or DAF. But before going to inverse FFT, let's see another kind of methods. So we have, apart from radix 2 FFT, we have radix 4 FFT and then split radix FFT and also mixed radix FFT. In radix 4 FFT, like the radix 2, we are splitting into two n by 2 points, right? Two groups we are splitting. But here in radix 4 FFT, we are splitting into 4 groups, 4 n by 4 point DFTs. N is divided into n by 4. So 4 groups will get. So and then it is applied for similar kind of butterfly diagrams. So these butterfly diagrams are little bit different, but same kind of operations only. We'll split and we'll add one time, and subtraction where we are doing subtraction, there we multiply with twin factors. By doing so, we'll get less number of computations, almost 25% lesser number of computations than radix 2 when in radix 4. So the constraint here is we must take the number of input samples must be in the power of 4. So we need to take n is equal to 4, 4 power 1, 4 power 2, 4 power 3, 4 power 4 and so on. And another one is split radix FFT. In split radix FFT, we'll use both radix 2 and radix 4 FFT. So if you use radix 2, we'll get one kind of computations, and radix 4 will get one kind of computation. So if you go and improve the radix, the complexity will be improved. So but complexity in the sense the complexity of method, but the computations will be fewer only. Split radix, it's an optimized way of performing this one with optimized complexity, and we can achieve the computations, less number of computations. Similarly, mixed radix FFT. In mixed radix FFT, we'll use different kinds of radixes, not only radix 2 and radix 4, we can use radix FFTs, other radix FFT. Now let's see the inverse FFT algorithm. What is inverse FFT? Inverse FFT means like it is to calculate inverse DFT. The method is in the reverse order will time. So in the reverse order means we will give x of k. We want to find out x of k. So inverse spectrum is given. We want to find out input sample. But the FFT, DAT FFT and DAF FFTs are derived by using the DFT formula, sigma x of n wn power k. But in the IDFT formula, x of n is equal to 1 by n into sigma x of k wn power minus k. It is wn power minus k will get. And apart from this, we will get 1 by n. So wn power minus kn means complex conjugate of wn power k. So in the actual formula, we didn't have wn power minus k, we have plus k. That means if you do complex conjugate of this one, it is equivalent to the DFT method. So when you do complex conjugate to whole, this sequence will also get complex conjugate. And this is x star of n, output is x star of n, but we want to get x of n. Finally, we'll do the output, whatever we obtain, that will be once again complex conjugated to get x of n. So before applying to the FFT algorithm, we'll apply a complex conjugate input, and then this twiddle factor will be same, because in the entire twiddle factor, entire derivation of DFT, we have used wn power plus kn only. That's why it is converted into wn power plus kn by applying a twiddle factor to the whole summation. And after obtaining final output, we can get back x of n by simply complex conjugate. Therefore, it has 3 steps. So first we have to complex conjugate the input sequence x of k to get x star of k, and apply forward FFT. We'll apply FFT algorithm. So whatever the FFT, if it is DAT FFT or DAF FFT, we can apply as required. the same flow chart we can apply, and we'll get the output as, so this summation only we are performing. This n can be sent to this side, so n x star of n, we'll get output as n x star of. So we are evaluating this summation only by using FFTL. So n f x star of n. So to get x of n from this one, simply we'll divide all the output samples by n and complex conjugate each sample. So there is this only few simple steps we want. So just input has to be complex conjugated, and then we'll apply FFT, either DAT or DAF, and the output octite samples are divided by, all the samples are divided by capital N, and all samples are complex conjugated once again. Right? So this is the way we use to find out inverse FFT irrespective of DAT or TAF method. And direct use of FFT. So we'll use IDFT with direct formula. In the same way, IDFT also having n square number of multiplication and n log n number of, n into n minus 1 additions. It is in the order of n square. But if you use this method, we'll use order of log n. So same number. Only additionally complex conjugation only we'll do at the input side and the output side. And all the outputs are divided by n. It's a constant division. Remaining all the complex multiplication and complex divisions are same as the FFT. Right? So if n is very higher value, so we can use two methods called overlap save method and overlap add method for finding the response of the systems we will use, but mostly. But FFT we will calculate as FFT algorithm. So now finally we'll arrive the FFT two methods for finding DFT as well as IDFT. In both the methods we'll use two kinds of FFT algorithms. That is decimation time, decimation frequency. Right. So that is FFT part, and so we can say this FFT is nothing but analyzing the signal in frequency domain, finding the spectrum in discrete phase. So this spectrum is very much required in most of the applications in orthogonal frequency division. So even now it needs 5G and 6G also. So in modulator side we'll use inverse DFT, and in demodulator side we use Fourier transform. So we need DFT and IDFT has to be performed. So if you use direct DFT calculation, it will affect the performance. So we use FFT algorithm. So wherever the Fourier transform is required to perform, definitely we can use FFT to perform it. In image JPs and image encoding, and radar and sonar applications where the range, Doppler range has to be calculated and filters needs to be applied there. So we need to process those signals by applying this spectrum analysis. And MRI imaging, and so this also required FFT algorithm. But it is 2D image. In image it is 2D FFT. We have to apply for row as well as column. So two pixels, two values has to be taken at different coordinates, XY coordinates. We want to locate the sample. So the input is an array, 2D array we need to consider. And spectrum analysis, and we need to use again the FFT one. And even power system analysis also, for finding the harmonics related to the power signal, we use this FFT. So the overall summary of this one is the complexity. The main important concept is reducing the number of complexity in finding DFT. So the number of multiplications are reduced by order of n by 2 log n, whereas in DFT it needs order of n square. The way we are performing is by using butterfly diagrams, DAT and DAF methods, where the inputs and outputs are just order is changing, but finally we'll extract it in the normal order. Okay, and we need number of butterfly diagrams or log n stages we need. So in each butterfly, simple butterfly, it needs 2 additions and 1 multiplications. So this will be repeated again. So it's a symmetric structure. In every stage we are having this butterfly diagrams. Okay. So by using this D8 butterfly diagram in DAT and DF, we can find out DFT. And similarly, the same concept can be used in finding IFFT also, inverse case, but only the thing addition operation is conjugation operation. That's about FFT. And so just go through the this kind slides. Quizzes are available in the website. Just go through the quiz again.